143. Finite Mathematics. Today we begin Chapter 7, Probability. So, probability is important because it helps us understand uncertainty and make decisions when outcomes are not known in advance. So, probability is important because it helps us to understand uncertainty and make decisions when outcomes are not known. We use probability in many areas, including weather forecast, medical studies, insurance, finance, business decisions, games of chance, and everyday risk assessment. In the first section, we will focus on the basic language of probability. So then, by the end of today's lecture, you should be able to define an experiment, identify outcomes and sample points, write a sample space, define simple, certain and impossible events, perform unions, intersections and complements of events, and determine whether two events are mutually exclusive. Okay, the basic terminology. Let's start with the experiment. So, in probability, an experiment is an activity that produces an observable results. So, in probability, an experiment is an activity that produces an observable results. For example, think about tossing a coin. Tossing a coin. So, if I toss a coin, I know the possible results, head or tail. I know the possible results, but I don't know which one will occur before I toss it. Right? Okay, what are the examples though? So, rolling a six-sided die. So, when I roll a six-sided die, I know the possible results. Number 1, 2, 3, 4, 5, or 6. But I don't know which one will occur before I roll a die. Drawing a card from a deck of cards. Drawing a card. So there are 52 possible results. The important idea is that the result is not known in advance. Okay, then let's move forward. The second word we wanted to know is outcome. So an outcome is simply one result of the experiment. An outcome is simply one result of the experiment. For example, if the experiment is rolling a six-sided die, possible outcomes are 1, 2, 3, 4, 5, 6. If the die shows 4, then 4 is the outcome of that particular experiment. For example, okay, then for a coin toss, and outcomes could be head or tail. Right? Head or tail. If the first coin toss shows head, then head is the outcome of that particular experiment. Okay, then next, we wanted to know a sample point. Sample point. A sample point is a single possible outcome of an experiment. Again, so in many elementary probability problems, the word outcome and sample point refer to essentially the same idea. In many elementary probability problems, both outcome, just a single outcome, and sample point refer to essentially the same idea. For example, rolling a die, when rolling a die, number 3 occurs. Number 3 occurs is a sample point. When tossing a coin, head appears is a sample point. Simply, as we discussed in the previous, one outcome, just an outcome, just a single possible outcome of an experiment is called a sample point. Both outcome and sample point refers the same idea. If it says outcomes, plural, that means all the outcomes, not the only single one. Next, sample space. So now we collect all possible outcomes together. So the set of all possible sample points is called the sample space. Set of all outcomes, set of all possible sample points is called the sample space. Sample space. So we usually denote it by using uppercase letter S. We usually denote it by using uppercase letter S. For coin toss, the sample space is head and tail. So keep this in your mind. When we write the sample space, we denote it using S. Also, we must write it within braces and comma separated. Within braces and comma separated. Head, tail. So very important. Within braces and comma separated. For six-sided die, for rolling a six-sided die, the sample space could be 1, 2, 3, 4, 5, 6. All possible sample points, all possible outcomes is called, the set of all possible outcomes is called the sample space of an experiment. Okay, next, finite sample space. The next word we need to know is the finite sample space. A finite sample space contains a finite number of outcomes. Simply, a finite sample space contains a finite number of outcomes. For example, one coin toss has 2 outcomes. One die roll has 6 outcomes. Drawing one card from a standard deck has 52 possible outcomes. All of these are finite sample space, right? Okay, let's say the example. If I toss a coin twice, what is the sample space? If I toss a coin twice, what is the sample space? Okay, pause the video and think about the possible outcomes. So first, I have the first coin toss. So two possible outcomes are head or tail, right? Then if I get the head for the first coin, then when we tossed after the first coin toss, when I toss the second one, it could be also head or tail, head or tail. So the possible outcomes are the first coin tossed with head, and the second coin tossed also can be head. Also, first one head, second one could be tail. First one tail, second one head. First one tail, second one tail. So the possible outcomes, are S sample space, head head, head tail, tail head, and tail tail. There are 4 possible outcomes. So again, you can see that head head, head tail, tail head, tail tail. So it is that head tail does not equal the tail head because the order of the tossers is different. Because the order of the tossers is different. Okay, then let's move forward. The events. An event is a subset of the sample space. An event is a subset of the sample space. This is where our work from chapter 6 becomes very useful. Suppose we roll one die, the sample space. Recall chapter 6 here. Then suppose we roll one die. The sample space is 1, 2, 3, 4, 5, 6. Define event A. Define event A as rolling an even number. So, what are the even numbers? 2, 4, and 6. Then, the event A could be 2, 4, 6. This is an event because it contains some of the outcomes from the sample space. Right? Okay. Next, simple event. The simple event or a simple event contains exactly one sample point. A simple event contains exactly one sample point. For example, the event A contains only number 4, means the event roll a number 4. Since it contains exactly one outcome, it is a simple event. Okay, then next, a certain event. A certain event is guaranteed to occur. That means the entire sample space. A certain event is guaranteed to occur. For example, when rolling a standard die, rolling a number between 1 and 6 must occur. So the certain event is the entire sample space. Next, impossible event. An impossible event cannot occur. For example, rolling number 7 on standard 6-sided die. There is no such outcome. Therefore, the event is empty. An impossible event cannot occur. For example, rolling a 7 on a standard 6-sided die. There is no such outcome. Therefore, the event is empty, impossible. Okay, when rolling a standard die, is rolling a number less than 10 certain, impossible, or neither? The answer should be certain. So rolling a number 8, impossible, right? So let's go for the quick check. When rolling a standard die is rolling number between less than 10, certain, impossible, or neither? The answer should be certain. Then what about the rolling and 8? Impossible. Right? Okay. Now up to this point we just discussed the terminologies for the basic probability. Then let's go for the operations on events. So we defined the events in chapter 6 and we are going to discuss the operations. So operations on events. Because events are sets, we can use the same set operations we learned in chapter 6. We will focus on, right? We will focus on union, intersection, complement. Okay, let's begin with the union of events. The union of two events A and B, A union B, means A occurs or B occurs or both occurs. Both A or B occurs. Both occurs, let's say the same as the set definition. Think about, suppose we roll one die. Suppose we roll a one die and let the event A could be 2, 4, 6. Event of rolling an even numbers. And let event B 5, 6. Event of rolling a number greater than 4. Okay, then A union B could be 2, 4, 5, 6. We include everything that belongs to either event, but we list 6 only once. So we include everything that belongs to either set either events, but we list 6 only once. A or B or both. Second, intersection of events. The intersection for both A and B events A intersection B means A and B occurred together using the same events A and B. A 2 4 6 rolling an even number, B rolling a number greater than 4. The only outcome that belongs to both is 6. The only outcome that belongs to both is 6. Therefore, A intersection B could be 6. 6. Next, complement of an event. The complement for event A as same as the set A complement contains every outcome in the sample space that is not in A. So if A is 2 4 6 is the event of rolling an even number, then A complement would be 1 3 5. This is the event of not rolling an even number. In other words, rolling an odd number. Okay, let's go for the one more example quickly. Example, suppose the event A 1 3 5 roll an odd number. Okay, find roll an odd number, and also B could be 5 and 6, number greater than 4. Roll a number greater than 4. Okay, then find A union B and A intersection B. Also, A complement. Find A union B, A intersection B, and A complement. Okay, let's begin with A union B. A union B, the answer should be 1 3 5 6. A intersection B, A intersection B 5. Only 5 appears in both. A complement 2 4 6, and B, let's say B complement 1 2 3 4. B complement. Okay, this is how the operations of event operations works as same as the set operations. For the events, we have sample space, the all possible outcomes. For the sets, we have the universal set. Okay, let's go for the mutually exclusive events. So, now let's introduce an important probability term. Two events are mutually exclusive if they cannot occur at the same time. Mathematically, we say that A intersection B equals empty. Another word for mutually exclusive is disjoint. I hope you remember that. We discussed the disjoint sets in chapter 6. So, two events are mutually exclusive if they cannot occur at the same time. Mathematically, A intersection B equals empty. So, another word for mutually exclusive is disjoint. They shared no common outcomes. Let's see the example. Let event A rolling number 2. Event B rolling number 5. Can a single die show both 2 and 5 at the same time? No. Therefore, the events are mutually exclusive. Okay, let's move forward. The next example. Example. Suppose we draw one card from the deck of cards, 52 standard cards deck. Let A, the event A, be the draw winner heart. Draw winner heart. Event B, draw winner spade. A single card cannot be both a heart and a spade, therefore these events are mutually exclusive. Okay, then let's see one more example, the non-example one. Let event A 2, 4, 6 rolling an even number. Event B 4, 5, 6 be the event roll a number greater than 3. Right? Then, are these events are mutually exclusive? No, because A intersection B could be 4 and 6, they overlap. Therefore, they are not mutually exclusive. Okay, then mutually exclusive does not mean unlikely. It means the two events cannot happen together. Then let's go for the exercises quickly. Toss in a coin, one simple event. Sample space, head and tail, one simple event, head. Rolling a die. Sample space 1, 2, 3, 4, 5, 6. One simple event. It could be any, but I choose 3. Right? Okay. True or false exercise. Statement 1. A simple event always contains exactly one outcome. A simple event always contains exactly one outcome. True or false? It's true. Statement 2. The complement of an impossible event is a certain event. Yes, it is true. The complement of an impossible event is a certain event. Yes, true. Okay, for the additional practices you can see the exercises. Okay, then let's go for the common mistakes. Before we finish, let's review some common mistakes because it is very important for the confusion with the experiment and the outcomes. The main thing is confusing the experiment with the outcome. The experiment is the activity and the outcome is the results of that activity. And sometimes confusing a sample space with an event. The sample space includes all possible outcomes. An event includes some of them. Confusing union and intersection. Union means or, intersection means and. Forgetting that complements depend on the entire sample space. Assuming two different events are automatically mutually exclusive, check whether their intersection is empty or not before say it is mutually exclusive events. Okay, then let's summarize today's lecture. Today we began our study of probability. We define an experiment, an activity that produces observable outcomes. We learned that the sample space contains all possible outcomes, while an event is a subset of a sample space. We also studied simple events, certain events, impossible events, unions, intersections, complements, and mutually exclusive events. The most important idea to remember is that probability uses the language of sets. Everything we learned in chapter 6 will help us understand probability much more easily. In the next lecture, we will begin assigning numerical probabilities to events and learning how probability values are calculated. Thank you for watching, and I'll see you in the next lecture.